Thank you. So first, thanks to CUNAMI and Petaspin to organize this workshop focused on scanning and magnetometry. It's quite nice that Rainer has already made a large introduction on the basic concept of scanning and magnetometry. So I will make it short on my side, just to remind that in fact this idea to build a magnetic microscope out of the single spin was early proposed by Chernebrot and Berman in 2005, where you have all basically the bricks of the microscope that are here. You have a nanoprobe at the end of an AFM tip. And what you do here, that you record magnetic field by recording the Zeeman shift of the electron spin sublevels through optical detection of the magnetic resonance. And just 3 years after this proposal, it tried to realize essentially that NV defect is somehow the ideal system to bring this idea to reality. So the principle of scanning NV magnetometry is depicted here. You have a single NV defect here that is placed at the apex of an AFM tip. And on top of this tip, hold on a second. Okay, so you have your microscope objective here that is used both to excite your single NV defect and also collect the photoluminescence that is produced by the defect. In addition, you bring a microwave antenna here that will be used to essentially measure the electron spin resonance by optical means. And then the idea is pretty simple. So you have this NV defect, you measure this electron spin resonance, and the splitting between the two ESR lines here is directly related to the value of the magnetic field projected along the NV quantization axis. This is the reason why here it's written BNV. This is a particular projection of the magnetic field that we probe in this experiment. So then you can bring a magnetic sample, any kind of sample, and then the idea is pretty simple. You will scan the sample, and at each point of the scan, record this Zeeman shift here of the electron spin resonance, and from this shift, build a magnetic field distribution. The key properties of this magnetic microscope is that it provides quantitative field measurement and also vectorial with a sensitivity that is in the range of a microtesla per square root of hertz. What is very important as well to compare magnetic field distribution with some simulation is that there is no magnetic back action like you could have, for example, in magnetic force microscopy. So you can easily consider that your sensing spin is not modifying at all the sample that you are looking at. It can operate from cryogenic temperature up to room temperature, even though in this talk here, I will focus on room temperature experiments. And what is very important here is to mention that the spatial resolution of the microscope is fixed by the distance between the NV defect and the sample that we are looking at. So even though the NV defect is an atomic size defect in diamond, which is somehow sub-nanometer in scale, the spatial resolution in the end is not limited by the size of the sensor, but rather by the distance of the sensor toward the surface. So there are two ways to engineer an NV defect at the end of an AFM tip. In early experiments, so first, let me first show you, sorry, the picture of our experimental setup. So here you have a tower of scanners that hold a tip here. And on the other side here, you have another tower of scanners where you can place the magnetic sample that you want to study. And on top of that, you have the microscope objective here, and you can see at the apex of the tip here, the focused green laser light. So as I mentioned, to engineer this single NV defect at the end of the tip, there are two options. In early experiments, we were doing that by taking nanodiamonds, so essentially particles that were few tenths of nanometer in diameter, and by gluing this particle at the apex of the AFM tip. This works, actually. This is what you can see here. This is a scan of the tip after grafting the nanodiamond, and you see that at the very apex of the tip, you see the emission here from a single NV defect hosted in nanodiamond. The drawback of this technique is that it's very hard to have a better probe to sample distance than something like 100 nanometers. So spatial resolution is limited to something like 100 nanometers. Another option is to rely on all diamond scanning probe tips that were introduced by the group of Amir Yacobi in 2012 here. So this is a picture of such a diamond tip. And essentially here, all the blue part here is made out of diamond, and there is a pillar here that has been created. And at the very apex of the pillar, a single NV defect is created by ion implantation. So there are many advantages of this technique. The first one, that it's extremely robust. You don't have the risk to lose the nanodiamond during your scan, for example, and also that you can bring your NV sensor much closer to the sample surface, essentially in a range of a few tenths of nanometer. So in the last year, this technique was brought to maturity, and now it's even commercially available by several companies, including Qnami, that is organizing this workshop. So since it is a workshop focused on scanning and magnetometry, I take the time just to give you one example of the different type of imaging modes that we can use to perform some magnetic field measurements. And for that, I take the one example that is an ultra-thin ferromagnetic layer. So it's here 1 nanometer thick cobalt layer with out-of-plane magnetic anisotropy. So the magnetization is pointing up. And essentially, we will bring our NV sensor to probe the magnetic field produced by this thin layer ferromagnet. And essentially, we will detect field at the position of a domain wall. As it was mentioned in some question, if you consider an uniformly magnetized magnetic wire, then there is no field produced. I mean, you need a divergence of the magnetization to have some magnetic field produced. And for example, that can be obtained at the domain wall where the magnetization is rotating. And this is also interesting because here in this experiment, you can imagine to infer what is the rotation of the magnetization at the domain wall position, which is directly related to some interfacial interaction at the interface between the cobalt layer and the substrate. So I will show you just few examples of magnetic image that you can do. And to explain you that, I just plot again here the evolution of the ESR frequencies as a function of the magnetic field. So from bottom to top, we just increase the magnetic field. And this is the position of the ESR resonances evolving linearly with the field. So one option, which is by far the fastest option to just have a rough estimate of the magnetic field distribution, is to apply a fixed microwave in the system. So essentially, you apply a fixed microwave frequency, and you collect the photoluminescence. Each time the NV defect arrives in a location of the sample where is this kind of field produced, in this case 14 Gauss, in that case the photoluminescence of the NV defect will be reduced. So this is what you see here. We scan the magnetic wire here, and we see some dark lines here that correspond to a measurement of an ISO contour, let's say an ISO line of magnetic field at this particular field. So you can also do that for a second microwave. For example, here, resonant with a region of 7 Gauss, and you have another field contour of your magnetic field distribution. And then to remove any kind of background or non-magnetic signal, you can just make the subtraction, and then you have a rough estimation of the magnetic distribution of the system that you are looking at. What is nice in that technique is that you just need to measure 2 frequencies to have your magnetic field image, and then you can make some repetitive images. And for example, in this case, you can see jumps of a domain wall between 2 pinning sides that is called Barkhausen jumps. And here you can see that with NV magnetometry in real space at room temperature with a nice spatial resolution. Here, essentially, the 2 pinning sites are separated by something like 200 nanometers. So this is the ISO-B imaging mode. And now if you want to take, let's say, the full power of NV magnetometry, then you can make a full B imaging mode. So in that case, you will measure the full ESR spectrum at each point of the scan and directly measure the Zeeman splitting. And in that case, you can record a fully quantitative magnetic field distribution. So this is the same domain wall here in this magnetic wire. And this is the field that you can detect from the domain wall. And what is very nice here, and I think this is one of the big advantages of NV magnetometry, is now that you can use this magnetic field distribution to compare with some theoretical prediction. And for example, here, one important point to address is to consider if how the magnetization is rotating at the domain wall position. And essentially, it can be either of a block type or a nail type. So what you can do is just simulate what would be the field produced by different type of domain wall structures, and then just directly compare with your experimental result. And for this particular case here, you can see that we have unambiguously and identify that this is a block domain wall. And then you can play around and changing some interfaces to change, for example, Dzialodziński-Mori interaction to find a way to stabilize nail domain walls or chiral domain walls by tuning the different interaction of the system. So this NV magnetometry technique has known a lot of application in condensed matter physics in the last year. I spoke about chiral domain wall in thin ferromagnets. It was also used to study the physics of magnetic skyrmions, but many other things, superconducting vortices as well. And we heard about two-dimensional material in the talk of Rainer, for example. And this is a picture from a work from Patrick Majetinski that I think he will talk about, where it is a monolayer of chromium triodide that is imaged with NV magnetometry. So in this talk, I was rather focused on another class of material, which are called antiferromagnets. So I think in this audience, I don't need to motivate that much why we are studying antiferromagnets. Essentially, in this material where neighboring moments are compensated, there are very nice properties for the design of spintronic devices. Essentially, one of the key points is that the dynamics of reversal of an antiferromagnet is in the terahertz range, while it's only in the gigahertz range for ferromagnets. So that opens the way somehow to the possibility to design some ultra-fast spintronic devices. So this is a kind of emerging field that is called antiferromagnetic spintronics, and that rely on these appealing properties of these materials for spintronics. Still, there is one important challenge here to address. So as I mentioned here, all the magnetic moments are compensated to first order. So as a result, the magnetic signals that are produced by this antiferromagnet are extremely weak, and it remains a challenge to image the antiferromagnetic order at the nanoscale. And actually, there are very few tools that you can use to make this challenging task. I just listed 3 of them with the spatial resolution mentioned at the bottom. So one technique that you can use is magneto-optic microscopy that is based, for example, on second harmonic generation. The idea here is that depending on the antiferromagnetic order, the second harmonic response will be different. And this is what you can see here. So this is an image of antiferromagnetic domains recorded by this SAG microscopy. And here, intrinsically, the spatial resolution of your microscope will be limited by diffraction. This is an all-optical technique, so it's limited by diffraction. To gain its spatial resolution, you can rely on X-ray, but for that, you need a synchrotron that is not really a laptop easy experiment to operate. And if you want even go to, let's say, atomic scale resolution, you have this very powerful technique, which is spin polarized STM, but this is only possible to use this technique for conductive samples. So and you need to be in ultra high vacuum condition. So the NV center in diamond comes in between here with a resolution of about 50 nanometer. And the key advantage here is that it can operate under ambient conditions and on any kind of magnetic sample. So in the last year, we have studied antiferromagnet with this ND magnetometer, and our favorite sample was bismuth ferrite that we heard about in the previous talk. This is a multiferric material that combines ferroelectric properties with a spontaneous polarization, here ferroelectric polarization, and it's also an antiferromagnet at room temperature. And the peculiar point of bismuth ferrite is that there is some magnetoelectric coupling in the system that promotes a cycloidal ordering of the antiferromagnetic order. So this is the cycloid that you can see here. And what is very important is that essentially that the cycloidal propagation direction, here K, is always perpendicular to the ferroelectric polarization. And that's interesting because essentially in this system, you can think about modifying the magnetic order by electric field, just by rotating the ferroelectric polarization. So this is something we did in the last year. So this is a collaboration with CNRS Thales in Paris, CA Aspect, and the Synchrotron Soleil as well. So this is an NV image of a thin bismuth ferrite sample. And you can see indeed that you have a cycloidal modulation of the magnetic field that mimic the cycloidal antiferromagnetic order. In that case here, you have the propagation that is perpendicular to the polarization. And as I mentioned, if you try to rotate the polarization by applying electric field, you can also rotate the magnetic order. So with this sample, then you can play around. You can look at how evolve the magnetic order when you cross ferroelectric domains. You can also study the evolution of the antiferromagnetic order while applying strain. So this is really a nice playground to use NG magnetometry and to try to understand what are the parameters at the origin of the antiferromagnetic order in this material. Other experiment has been done in another antiferromagnet, chromium oxide, that I think Patrick will speak about that later on in his talk, with 2 recent papers dealing with measurement of domain walls in this CRTO3 sample. So here, this slide shows you that indeed you can use ND magnetometry to image antiferromagnetic order on the nanoscale, but still there is a limit to that, is that you need to rely on an antiferromagnet that is not perfectly compensated. If you now consider a perfect antiferromagnet, there is no uncompensated magnetic moment, and in that case, there is no magnetic field generated. In the case of bismuth ferrite, in the cycloidal rotation, there is always a tiny uncompensated magnetic moment. And this is essentially what we measure with NV magnetometry. Now you could think about some samples where such uncompensated magnetic moments are too small or too weak to be detected. So now we would like to think about another alternative technique that could help to image some spin texture in perfectly compensated antiferromagnet, or at least in antiferromagnetic material where stray fields are too weak to be detected by the NV magnetometer. So the idea we will follow was proposed by Jaroslav Tarkovniak in 2019. So the idea here is not to measure the static field produced by the antiferromagnetic spin textures, but rather the magnetic noise that they produce. So essentially, on average, the field is zero, but there are fluctuations, magnetic noise, that we can probe with a quantum sensor. Here, that will be the NV defect. So the idea is the follows. We have an antiferromagnet, right? And there is, for example, as you can see here, there is a domain wall here in the antiferromagnet. And the idea is just to come with our quantum sensor and to measure magnetic noise. And in this paper, what is mentioned is that if you go on a domain of the antiferromagnet, you have a certain amount of noise, some thermal agitation of spin waves or magnons. But now if you go at the domain wall, there is an excess magnetic noise because you have additional magnons that can be populating. And as a result, you have additional magnetic noise. So the idea is pretty simple. It's just to use the NV spin to measure magnetic noise above the antiferromagnet and localize textures like domain walls or skyrmions or whatever by detecting the magnetic noise they produce. So I need to tell you a bit how we measure magnetic noise with the NV sensor. So for that, I need to come back a bit on the basic properties of the NV defect. So just they are reminded here. Everything happens in the ground state of the NV with a zero field splitting here between ms equals 0 and ±1 by something like 2.8 gigahertz. So this is the zero field splitting. And what is very important is that when you shine green laser light onto the NV defect, there is an efficient polarization of the spin in ms equals 0. So essentially, just by shining light on the NV defect, we can break the Boltzmann distribution and efficiently polarize the system in ms equals 0. In addition, this ms equals 0 state is a bright state, meaning that we will emit, the NV defect will emit much more photoluminescence when this state is populated. Okay. So let's consider as a starting point that the NV defect is prepared in this bright state, ms equals 0, and then we switch off the laser and we wait for a free evolution. After a certain time, the system will relax and come back to the thermal equilibrium that corresponds to equal population, spin population in all the different spin sublevels. And the characteristic time to reach this thermal equilibrium is called T1. This is the longitudinal spin relaxation time. And what is very interesting is that this T1 time somehow is inversely proportional to the noise density at the electron spin resonance frequency. So essentially, if you have noise at this F0 frequency, that will boost relaxation. Relaxation will be done much faster. So just to give you an example, how we measure. So this is exactly like that. So there is the first laser pulse here that essentially prepare the system in ms equals 0. Then we wait for a free evolution during a time tau, and then we read out the spin state through a measurement of the spin-dependent photoluminescence signal. So this is a typical result that you can get when there is no noise. So you have a decay of the signal here over an exponential decay with a typical time scale T1 here on the order of 1 millisecond, which is the usual T1 time that you can obtain from single NV defect at room temperature. If now you have a noise source close to the NV defect, then the T1 time drops. So the idea, this is called spin relaxometry. The idea here is just to measure magnetic noise by measuring the spin relaxation time of the NV defect. And in the last year, this has been applied to many different systems. For example, the detection of Johnson noise in metal, so essentially fluctuation of electrons that produce some fluctuating magnetic field. It was used to measure also and you study spin waves and also to detect magnetic nanoparticles. But now if we want to make this kind of measurement in an imaging mode, meaning that we need to measure T1 at each point of a scan, this is extremely long to perform because to measure such a T1 here, essentially you need a couple of hours. So you cannot imagine making a T1 measurement at each point of the scan in order to infer what is the magnetic noise. So we need to rely on another mechanism to measure the magnetic noise. And I will show you just in this slide that we can just measure the photoluminescence signal without measuring the full curve, the full T1 curve. So again, I come back a bit on the NV defect in itself. So coming back on the ground state spin structure here. And essentially what you need to consider is essentially two rates. In green here, what's the rate gamma P, with essentially the rate at which you can polarize the system in MS equals 0. I told you that under optical pumping, we can polarize the system in MS equals 0. This is done with the rate gamma P that evolve with the optical pumping power, okay? And that pumping process is competing with gamma 1, which is the spin relaxation rate, okay? So then there are two cases, essentially, extreme cases. In the first case, you can consider that gamma P is much larger than gamma 1. In that case, pumping is very efficient. You end up with all the population in MS equals 0, and as a result, you have a high photoluminescence signal. On the other hand, if gamma 1 takes over gamma P, in that case, you don't have efficient polarization anymore, and you have some population that remains in the dark state. As a result, you will get a lower photoluminescence signal. So if you make very simple rate equation, you can plot the photoluminescence signal as a function of T1, and you see that the PL signal is decreasing with T1. And this is for a given optical power. If you increase the power, of course, you increase gamma P, so the drop of the photoluminescence will occur at shorter T1. So you can directly see here that we have another way to measure magnetic noise that is very simple. If there is noise in the location of the NV defect, that will lead to a drop in T1, and this drop in T1 will lead to a drop of the photoluminescence. So this is this basic principle we verified by just applying a calibrated magnetic noise, and this is what you see here, where we record the photoluminescence as a function of T1, and indeed, you can see that you have a decrease with something like by about 10 to 15% of the photoluminescence when T1 is decreased. So, and we will use this contrast here now to image magnetic textures in antiferromagnets. So the sample we want to look at is a synthetic antiferromagnet. So it's two ferromagnetic layers that are coupled antiferromagnetically through a non-magnetic spacer here. So it's not a real antiferromagnet, but it's a kind of model system that can be used to emulate the physics of antiferromagnet. And what is nice in this system here is that you can really tune all magnetic properties of your sample by just tuning the thickness of the different layers. So this is the composition of the stack, and this samples are perfectly compensating, meaning that the cobalt layer here, which are the ferromagnets, have exactly the same thickness. And this sample have been optimized by the team of Vincent in the CNRS during the PhD of William Legrand. And essentially, this sample, it was the first time that it was possible to observe antiferromagnetic skirmings. So we take first a sample in which the thickness of the cobalt layer has been chosen in order to have some anisotropy in the system that could stabilize domain walls. And then we take our diamond tip. So this is a tip here from Tsunami here, the NV at the apex. And in this case, we don't need any kind of microwave excitation. We just record the photoluminescence signal. So this is a typical image that we can get. And you can see here dark lines here that correspond to the position of domain walls in the system. So essentially here, at domain walls, there are a lot of magnons that are thermally activated that produce magnetic noise that leads to a quenching of the photoluminescence. To verify that this quenching of the photoluminescence is indeed related to a modification of T1, we perform some local T1 measurement in two different cases. On the first case, and this is the blue curve, we bring the NV tip above a domain, right, of the synthetic antiferromagnet. And here we end up with a T1 of about 120 microseconds. And in a second experiment, we bring the NV spin just on top of the domain wall. And in that case, you can see that you have a strong reduction of T1 that corresponds to the magnetic noise generated at the domain wall position. So this experiment shows that the PL quenching that we are seeing is indeed coming from magnetic noise. So regarding the origin of the noise in itself, we relied on micromagnetic calculations that were performed by Jovan Kim at the C2N in Saclay, where essentially Jovan calculated the dispersion relation of spin waves both in a uniform domain and at a domain wall. Okay, so this is a typical dispersion relation of spin waves in a uniform domain for our synthetic antiferromagnet. And you see here that at the electron spin resonance of the NV defect, at this F0, you cannot excite any magnets. So essentially, you don't have magnets in the systems that will produce a noise at the ESR frequency of the NV defect. And in that case, there is no noise that can be detected by our quantum sensor. If now we make the same calculation at the domain wall, then the dispersion relation is gapless. And this is something very general for domain walls in ferromagnet as well. And you can see that there will be a lot of magnets that can be populated that have the good frequency and that will produce some noise at F0. If you even calculate what is the noise map at F0, so at the ESR frequency of the NV defect, you can see that indeed at the domain wall position, you have an excess magnetic noise, and this is what we measure in our experiment. So as a last slide, what I want to show that you can do a bit more than domain walls. Playing with a synthetic antiferromagnet, you can tune the cobalt thickness in order to have a sample with vanishing anisotropy. And in that case, you don't expect isolated domain walls, but rather a spin spiral. So this is what we measured in this same relaxometry mode. You can see here the spiral that has the good periodicity. Since you have this spiral, then you can turn the spiral into skyrmions. And for that, you just add a bias layer here that will act as an internal magnetic field that will destroy the spiral and stabilize some skyrmions in a synthetic antiferromagnet. While doing that, again, with the NV relaxometry image, you can see some isolated dark spots that correspond to a skyrmion in a synthetic antiferromagnet. Okay, I'm done. So just to conclude, I've shown you that we can use this NV defect not only for measurement of static magnetic field, but also magnetic noise that might have some application for studying some magnet modes localized at domain walls, for example. But as it was mentioned in Rainer's talk, you can also imagine to use the sensor for electric field imaging and also for temperature imaging. So this is a kind of multimode sensor that can find much more application than the one that we're discussing in this talk. I want just to thank the people involved in this work and all the collaboration that we have with people expert in spintronics to make all this work together. Thank you.